So welcome to Budapest. When you hear news about Hungary, it's often quite controversial. However, there's one thing that Hungarian mathematicians can be proud of with no reservation, that we have two Hungarian Nobel Prize winners, and both of them work in combinatorics. One of them is László Lovász, who is largely responsible for shaping what we call modern combinatorics today. So he definitely needs no introduction. Or does he? So who are these handsome young men looking so optimistically into the future? So let me help.
I know all of them. Yes.
They are a subset of students at Fazekas Gymnasium Budapest. All of them knew Erdős and Hajnal already as high school students, and all have become world-class mathematicians. So I think that this is a great illustration of the importance of education in mathematics. In fact, most of those young combinatorists who we have now in Hungary were to some extent students of Lajos Pósa in elementary school or high school, and the students of László Lovász at the university. So let us welcome László Lovász.
Well, thank you. And thank you very much for the introduction. I hope it's my slides are okay now. You see them?
Yes, it's perfect.
Okay, thank you. So these are two topics I have liked in my research, and returned to both of them repeatedly, and recently there some rather unexpected connection has come up, and so I would like to report on that. But first, let me talk a little bit about this idea of orthogonal representations. This is old construction. So you take a graph with node set V, and to every node of the graph you associate a vector in D space. And the condition is that if two nodes are not adjacent, then the corresponding vectors must be orthogonal. Usually it doesn't make much difference if you assume that all the vectors are unit vectors, so that they are on the unit sphere. And it's just two illustrations of such a representation. If you can, here you can take two clicks which cover the graph, and to a click you can assign the same vector because there's no condition on the vectors in the nodes of the click, and so therefore you get just in two dimensions you get a kind of trivial representation. And the non-trivial representation you can get, say, taking a pentagon and representing it by the edges of this pentagonal pyramid in 3 space.
Lassi, the U and V are the same or not?
Oh, sorry, yeah, U and V are the same, yes. Okay. Yes. Now, there are many questions you can ask about orthogonal representations, and they tend to have interesting connections, and I'll show just two of these external connections. You can try, I mean, if you have always, if you go up to a high enough dimension, you have such an orthogonal representation, but you have to put some limitations or try to be economic about it. And one possibility is to try to squeeze them into a small cone. And that leads to the definition of something called the theta function. And I'll show you an interesting application of this in quantum physics. And or you can, instead of squeezing them in a small cone, you can squeeze them in a low dimension, in a fixed dimension. It is usually a very difficult question of which graphs have representations in some fixed small dimension, but we'll see that if you impose the condition that the representation has to have a general position, then you get interesting results which have applications, and I will show you one application in the theory of rigidity of structures. And the new things are about trying to construct orthogonal representations at random. And that turns out to be a quite interesting question. And it is very closely related to some basic unsolved problems in graph limit theory. And so I would like to talk probably about half of the time about this. So let's try to squeeze them in a small cone, and I don't care about the dimension here. And say alpha is the half angle of the smallest half angle where you can get an orthogonal representation within this cone. And then you can define theta of GS, well, as basically this alpha, but it's better to take 1 over the cosine square of this alpha. There are many other definitions, and I won't go into this. What is important about this number is that it is always an upper bound on the maximum independent set of G, since an independent set has to be represented by mutually orthogonal vectors, and it's very elementary what is the smallest cone that you can get alpha mutually independent or A mutually independent vectors. And it's bounded from above by the chromatic number of the complement, which is again easy if you think about the first construction on the here. So you basically, the chromatic number of the complement means covering the graph by clicks, and so this construction generalizes and gives this upper bound. And of course, the interesting fact is, which I probably should mention, is that the maximum independent set in a graph G and the chromatic number in terms of the complement are very interesting numbers, but they are NP-hard numbers. And what we have here in between is polynomial time computable. This has various applications, among others. This is probably the only known way to compute the chromatic number of a perfect graph. Now, but I would like to talk a little bit more about this application to quantum physics. So here is a crash course on quantum physics. The state of a physical system is represented by a vector in Hilbert space in quantum physics. A measurement on this state is performed by applying a self-adjoint linear operator to this, and then the possible results of the measurement are the eigenvalues of this linear operator. Observing an event is a measurement, is a very special measurement where the outcome is either yes or no, or 0 or 1. So that's a projection onto a one-dimensional subspace. And the probability that an event is observed is then that the event actually happens or is observed as true, as valid, is the squared length of the projection of this vector representing the state onto the vector representing onto the one-dimensional subspace representing the measurement. And finally, this is a little bit vague, but if there are several events, and we know in quantum physics that you cannot necessarily observe everything. So once you observe something, it changes the state of the system, and you cannot observe maybe something else. And in fact, if certain events can be simultaneously observed, then the corresponding, remember, events correspond to one-dimensional subspaces. The corresponding one-dimensional subspaces are mutually orthogonal, and vice versa. And if there are any physicists attending my talk, then I will probably get a terrible sort of reactions to this, because it's a very vague and probably absolutely incorrect. Every line here is incorrect, but let's accept this. Now, this last line sort of brings up the idea of orthogonal representation. So we will have here vectors, A1 and so on, and these vectors have to be, some of them have to be orthogonal, and so that means it's an orthogonal representation of a graph where an edge means that those two events cannot be simultaneously observed, which is more or less the same thing as saying that they cannot simultaneously occur. Now, the theory that this is related to one representation of one consequence, I should say, of orthogonal representations concerns the theory of hidden variables. So if you take, so again, in a nutshell, you can take two electrons and they will be in some quantum state, which is a up or down or some kind of linear combination of these two states with complex coefficients. And you can entangle them, which means that they will be sort of in the same quantum state. Individually, they can still be in any state, but the other one will be exactly in the same state. So that's what we call an entangled pair of electrons, or it's an EPR pair. EPR stands for Einstein, Podolsky, and Rosen. Now, this pair of electrons, then actually we can give it to our two favorite characters, Alice and Bob, and they can travel. One goes to Mexico, the other one goes to New Zealand, and they still have the electrons, and if they carefully defend the electrons from any external influence, then these two electrons will remain entangled. And then if Alice looks up her electron, then it will, from this quantum state, will become, the measurement says that no, it's up or it's down. And Bob, then Bob's electron will also be in the same state. And that is mysterious at first sight. It looks like this is a communication faster than light. Then one can argue that this cannot be used to any kind of communication, but it's still a very interesting thing. So they sort of jump into the same state. Now, one possible explanation for that is that actually these electrons have some kind of complicated internal structure, which we don't know. And internal doesn't mean that it has to be inside the electron. Maybe it has all sorts of connections all around the world. And the two electrons are in the same internal state. And therefore, of course, if you measure something on one and you measure something on the other, it will always be the same. And this is called the theory of hidden variables, which was used for a long time to disprove various facts about quantum physics, or to explain it in terms of more classical language, I should say. Now, these physicists have discovered some interesting connections of this to orthogonal representations, and let me go on with saying a few words about this. So this is called Bell inequalities. It's not exactly the classical Bell inequalities, which are connected to disproving the theory of hidden variables. But let's think of this as a graph. So we have a graph, and suppose that each node of the graph is either black or white. Actually, it's in a quantum state, which can be either, which is a combination of being in black and white. Okay. And an edge means that they cannot be both black. So that the event that this is black cannot occur simultaneously. But we cannot observe all of them because they are not necessarily orthogonal. And in fact, let's say we can only observe one event of all of these. And so we observe one of these events, we don't know the others, and this is, say, black. Or maybe it is white if we observe another event. But we cannot make these two observations simultaneously. However, we can do to repeat the experiment many times, always picking a random node and observing it. And then the question is, how often do we see black and how often do we see white? Using the hypothesis of hidden variables, we get that the probability that a node is black is bounded by the independence number alpha of G divided by number of nodes N. Because at any particular repeated experiment, the theory of hidden variables says that those nodes are in the black or in the white state, except that we don't know which one, but they are. So if you observe one of them, simultaneously there can be at most alpha G black nodes. So if you pick a random, the probability that we see a black is at most alpha G over N. Now, if you use just quantum physics, then the probability that you see black node can be larger, but you can still derive, not very hard, that it's at most theta of G over N. Now, these two bounds are different if the graph, if theta is only an upper bound than alpha of G. And so to disprove the theory of hidden variables, what you need is a graph for which this value will be larger than alpha of G, hopefully not less than theta of G. That would disprove the whole quantum theory. And this is an experiment you can actually perform. And well, there are various graphs have been used. For example, probably the most popular one is the Wagner graph, which is a graph on 8 nodes as depicted here. This says alpha of G equals 3, and theta of G is 2 plus square root of 2, so it's larger than 3. So the question is, what happens if you somehow realize this graph? Now, that's the non-trivial part, of course, to create an experiment where these this will be exactly the structure, but it can be, in fact, just observing an EPR pair in an appropriate way. You can create this graph of describing the results, possible results of the experiment. And here is actually a report. There are many people who have done this or similar experiments, and even the physical setup with over a kilometer far, Alice and Bob being at almost a kilometer far has been reported. So here is this graph, and here are the experimental results. The hidden variable theory would imply a probability of at most 3.3738, and quantum physics implies 0.427, and the experiment turned out to be 0.401. It's almost exactly halfway between the two values, but it's certainly larger than the first one. So this can be considered as a disproof of it. It is not clear whether you can modify the experiment and to actually get close to the second bound. That would be interesting, because it would mean that this upper bound in terms of theta g is actually a physical reality. Okay. Now, this has been the first application, and it's about orthogonal representations. Let me talk about orthogonal representations in a given dimension. And I will not be very long, but I have to quote a result, an old result with Lex Scriben and Mike Sachs. And it says that if G has an orthogonal representation, that G has an orthogonal representation in general position. So that means any D vectors are linearly independent in D space, if and only if it is n minus D times connected. That will be important. And so let me just very briefly describe the application of it. So you want to construct a bar and joint structure in this space, which is globally rigid. That means that it's not only it cannot move, but there is no other non-congruent structure which has the same edge lengths. So here are three examples of such structures. The middle one is supposed to be on one line, but we had to draw it a little bit distorted. And the middle one is not in general position, but the right one, for example, is in general position. And the theorem of Al-Faqih says that this is doable if and only if G is D+1 times connected. And the only interesting fact here about this, why I am pointing out what I'm pointing out, is that this is the previous result was about connectivity, n minus D connectivity, or in other words, maybe D+1 connectivity would give a representation in dimension n minus D, or n minus D minus 1, whereas here it's in the same dimension. So that's not the orthogonal representation, but one uses the orthogonal representation to prove that the construction is, whatever is the construction is globally rigid. So you take this representation in the condition says that it's in n minus D minus 1 dimension, general position orthogonal representation, and then you take the Gram matrix of this representation and then use this as a kind of proof of rigidity of the construction, so that it's somehow the logic which will move from n minus d dimension to d dimension. Okay, now let me come to this homomorphism. So it will be more convenient from now on to talk about, instead of orthogonal representations, about orthohomomorphisms or homomorphisms into the orthogonality graph. The orthogonality graph is what you think is a graph on, it's an infinite graph on the points of a sphere, a d-dimensional sphere, and the edges are connecting orthogonal pairs of points. So that's then an orthogonal representation of G means that non-adjacency goes to orthogonal. So in terms of the complementary graph, adjacent pairs go on to orthogonal. So you get a homomorphism in the orthogonality graph. And in terms of this, this result that I have already talked about, it's just basically says that G has a homomorphism into HD if and only if, and n minus d connected in terms of the complementary graph means that it does not contain a complete bipartite subgraph on d+1 nodes. So it puts a bound on how large a complete bipartite subgraph can be in this graph. So this is just the same theorem rephrased in terms of the complementary graph. Note that this implies in particular that the all degrees are at most d-1. Now, crash course on graph limit theory. Suppose that we have a sequence of graphs which are larger and larger finite graphs, and they become more and more similar. And we would like to ask, I call it a template for large members of this sequence. So believe that they become more and more similar in some sense, but they should sort of be more and more similar to one particular structure, which is, I call a template. Now, to be more specific, we have to define what does it mean, more and more similar, and this needs some kind of definition of convergence. So this leads to the notion of convergence of this graph sequence. And basically, there are two kinds of convergence considered here. Left convergence means that we look at the local structure of these graphs, for example, the number of triangles or number of edges, or average degree or something like that. And they have to become more and more similar from this point of view. And right convergence means that we map them into some other graph or some other structure, and then we study these maps. So for example, the chromatic number of these graphs is just the smallest complete subgraph into which they can be mapped homomorphically. So chromatic number would be could be part of some definition of right convergence. And then you would like to construct a limit object that is a template. Now, of course, you always have a kind of abstract limit object, just equivalence class of convergent sequences, but we would like to something specific, some well understood limit object. And there are two cases which have been studied to reasonable depth. And one is the case of dense graphs, so graphs which have a constant times n squared edges with n nodes. And for them, there's a very natural notion of convergence. You count homomorphisms from a fixed graph F and divide it by the total number of maps from the fixed graph F into the node set of G. So this is the probability that a random map of the nodes of F into the nodes of Gn is a homomorphism. And if this sequence, this convergence as n tends to infinity for every F, then we say that the graph sequence is convergent. And the limit objects to this are graphons, which are just very simple objects in a sense. They are measurable symmetric functions from the unit square into 0, 1. And the other well-studied case is the case of bounded degree graphs. Now, it turns out here there are several highly non-equivalent notions of convergence. There's the Benjamin-Schramm or local convergence. There's something called local global convergence, scaling convergence, and so on. And also there are several notions of limit objects, of which I will be interested a little bit, but only as a motivation, graphings, which I will not define. It's more complicated. They are certain Borel graphs with bounded degree. And this is just the motivation. Rather well worked out cases, the two extreme cases, but what happens in between? And that's kind of the holy grail of graph limit theory, but what happens in between? So what is common in the limit structure? So let's try to guess what limit structures should be. They all have a Borel sigma algebra, like mostly the 0, 1 interval and the Borel subsets of the 0, 1 interval, but sometimes it's more natural to talk about Borel subsets of some other reasonable space, like spheres or cubes. And that is a node measure, which corresponds to being able to select a random node. And then there is an edge measure, which is says that we are able to select a random edge. And what I would like to propose now, that we just try to see what is included in this very simple structure. So there is a simplest possible non-trivial sigma algebra, Borel sigma algebra, together with a node measure and together with a symmetric edge measure. In fact, I will even restrict my attention for regular graphs, to regular graphs, which means that the node measure is just the marginal of the edge measure. So the edge measure is a measure on pairs, on Borel sets of pairs, and the marginal of this means we pick a random edge and then we pick a random endpoint, and in the case of regular graphs we get a random node. So the node measure is the marginal of the edge measure, so we don't have to worry about the node measure. And so we come to the notion of a Markov space, which is a Borel sigma algebra JA, and there is a probability measure on the square, which has both marginals equal. In fact, as long as we want to stick to undirected graphs, we can assume that this measure is invariant under interchanging the coordinates. So it's a symmetric measure on the unit square. And this turns out to be the same, essentially, as a Markov chain with a specified stationary distribution. So it's a very well-known structure. It's a much studied structure. Maybe I'll come back for a second. So these are the two examples. So you see here there is a measure on the unit square, and this measure for graphon is a nice absolutely continuous measure with respect to the Lebesgue measure, while these graphings, which are also measures on the unit square, but they are highly singular measures. concentrated on essentially a one-dimensional subset. So these are different notions, but both of them are measures on the unit square. So here are the basic questions about Markov spaces. How much of graph theory extends to Markov spaces? And in fact, a lot of it can be. It turns out, for example, that flow theory has very nice and natural extensions to Markov spaces. Of course, random walks on graphs, spectral theory, and a number of other things have natural extensions to Markov spaces. But you can ask now which sequences of regular graphs have limits as Markov spaces. So what kind of convergence notion leads to limits as Markov spaces? And then, of course, you can ask the inverse question, which Markov spaces are limits of graph sequences? This is not an easy question. I mean, in the dense case, it's okay. All graphons are limits. But in the graphing case, that's a famous unsolved question of sophicity or Aldous-Lyons conjecture, that every graphing is the limit of locally convergent graph sequence. So neither of these questions is easy. Now about convergence to Markov spaces, there are examples, and I am just as a reference putting here some keywords. Shape convergence, which is basically a notion of right convergence, was introduced by David Konstanty-Kovács and Balázs Szegen and myself. And limit objects can be represented by Markov spaces. Action convergence, also in a sense a notion of right convergence, was studied by Ágnes Backhaus and Balázs Szegedy, and again, the limit objects are Markov spaces. And then Peter Frankel has some other notion and constructions of limit objects which are related, but I will not talk about it. And but that was a notion of left convergence. And so here is a recent work with David and Balázs that I would like to talk very few minutes about. So here are these two co-authors of mine. And so once you want to define convergence in terms of subgraph densities, it's a must to define subgraph densities in the limit. So subgraph densities in the sequence must converge to the subgraph density in the limit. And it turns out that this is a rather difficult question. So how to define subgraph densities in the limit object? So subgraph density traditionally is defined. I just already defined that. Trouble with this is that once the graphs are not dense, everything tends to zero. So this density tends to zero. So we need another normalization, and so we normalize this in terms of the density of the edge to an appropriate power, which is the number of edges in F. We denote this by T star. And this does not necessarily tend to zero, and this has some interesting properties, at least for subgraph densities which are of the order of a power of n higher than 1, so 1 to the n to the 3/2, say. But this is it's a very interesting notion itself, because it relates the famous Sidorenko-Szymonovich conjecture, which says that if F is a bipartite graph, then its density in any graph, this T star density, is at least 1. So it's a very simple formulation of this conjecture. Now, so let's renormalize. So we take a graphon now, and we renormalize it so that all the intervals, the integrals, if you integrate out one of the variables, you get one. So this will not be between 0 and 1 necessarily, but we still have a bounded measurable function like this. In this case, the old and new notion of subgraph density will be the same. It can be shown that this is always 1 if t is a 3. And you can even define a random homomorphism in this case, which is simply the you have to the weight function. If there's a density function of it, which is the product of the edge weights. Okay, so I think I should stop in a minute or two. So let me just give you the key idea. So you want to define subgraph densities in the orthogonality graph, and you want to want to define a sort of random image of a graph, a finite graph in the orthogonality graph. Now, starting with a triangle, this measure, this random, this probability measure is trivial because they are all isomorphic, so they are, you can sort of take, there's a notion of a uniform distribution over that. It turns out that to define the density of them in this graph, T star is non-trivial, but it leads to interesting results. And C4 creates a trouble because think of trying to map C4 into the usual two-dimensional sphere. So the two red edges on the here on the upper left corner are already there, and let's try to complete this picture to an image of C4. Well, the fourth node has to go either on the North Pole or on the South Pole. So I'm thinking of this dotted circle as the equator, because that's the only point which is orthogonal to both of them. So this means that all the maps fall into two categories. Either one pair of opposite points are mapped degenerately on parallel vectors, or the other one. And so there is no natural notion of a random copy of K4 or C4 in here. But actually, once you go up to C5, then the result, then there is a non-trivial but doable notion, which a nice notion. And I just finish with showing that with a lot of work, you get actually some kind of really interesting formulas for these densities. So the density of K3 or C3, so the triangle is 2 over pi in 3 space, it's pi over 4 in 4 space, is 8 over 3 pi in 5 space, and so on. These are still a little mysterious, but let me stop here, and maybe you can see that there is some quite unexpected connections here, and we are trying to finish this. So thank you very much for your attention.
Thank you very much, Laci, for the beautiful talk. We have some time for, little time for questions, but maybe 1 or 2 questions, if anyone.
Yeah, I have a question. I wonder, so is it possible to get some new results for Markov spaces by using results from graph theory and getting Markov space to which a sequence of graphs converges, or vice versa?
Well, certainly as a motivation, you can have that. For example, flow theory gives interesting results, which it seems that they were not known in the theory of Markov spaces. Of course, you always have to be careful with such a large theory. So, but it seems so. For example, the Hofmann circulation theorem, Max Flow-Minkat, the multi-commodity flow theorem, they have very nice extensions to these. So in this sense, you get at least motivate. They need separate proof, but the motivation there. I think it's this connection should indeed be yield more, but at least something is there.
Mm-hmm. Okay, thanks.
Thank you.